Well, hello everyone, and welcome back to Adrian's Digital Basement. I just recorded an entire intro sequence without hitting record on the camera, so I'm gonna have to do it again, which is what you're watching right now. So if you watch my channel regularly, you know that I absolutely adore and I love CRTs. There's something about using these things with their old computers that they were designed to work with, or game consoles, that just brings a really warm and fuzzy feeling to my heart. Just the memories of staring at a glowing, flickering monitor while I used computers back in the 80s or game consoles, it just is something really special about it. And even though I know how monitors work, I still feel that there's a lot of magic going on inside here. There's high voltage, there's electrons flying at a phosphor screen, magnetism moving the electron beam around. There's just some really cool and intricate stuff happening inside of monitors. And let's be honest, monitors are wear items, so as you use them, they wear out, but also they are never going to be made again. So what we have on the planet now, the monitors that exist now, the TVs and monitors that is it. The tooling and the machinery that makes these things, especially the glass CRT, will never be made again. Unless we come up with some Star Trek replicator style technology that could then replicate working monitors, I don't think we're ever going to see any more of these, at least not in my lifetime. So that's why whenever I see a monitor that's broken like this one that is about to be recycled, I like to try to save it so I can hopefully get a working monitor out of it, but also show other people that it's possible to fix these things. Now, back in the day when televisions were CRT-based and computer monitors were CRT-based, we had repair shops all around that allowed you to take your stuff to them to be fixed. Unfortunately, it's not economically viable to do repairs on modern displays. You just throw them away and buy new ones. And therefore, all of those shops have long since closed, or almost all of them have. And unfortunately, a lot of the knowledge about repairing CRTs day in and day out, unfortunately, is just not with us anymore. The folks that did that work either have retired or they have passed away, unfortunately. And that means all that skill and knowledge they learned repairing these things over the years, that's just gone. And the disappearance of these people and the shops all happened before we really had the internet and YouTube. So that just means there's less information out there about getting these things working. Well, since we can't just walk down to the computer store and pick up a new computer monitor, it's worth trying to save these things. And that's what I'm going to do in this video. I want to take a look at this monitor, which looks pretty cool. It's a pretty cool design, actually, for a beige computer monitor. But we want to open this thing up, take a look at what's going on inside, and see if I can figure out what's wrong with this thing, and maybe get this thing working again. There's always no guarantee with CRT repairs, because sometimes the component that's broken might be something that's not replaceable, and therefore this monitor will definitely become scrap. Well, in that case, I'll be saving the CRT because this part is transplantable into other monitors, but the rest of the monitor will become scrap. All right, well, that was a long enough intro. So without further ado, let's get right to it. This monitor was sold by the company Leading Edge, and I've had several PC archaeology episodes where I've focused on leading edge computers. And I know that there were a lot of people whose first computer was some leading edge PC, and I'm going to wager that a bunch of people watching had one of those computers paired with this exact monitor. Now, I have to admit, as far as beige computer monitors go, this is a really interesting design. It has a kickstand on the back which allows you to tilt the monitor up, and if we rotate this around to the other side and notice the huge bundle of cords which I have tucked under the monitor, there's a button you can push that frees up that little kickstand, and when you let go of the button, it actually locks in place and allows you to adjust the tilt of the monitor. Very cool design, but the fact that the entire top of the monitor is flat is just really interesting. It's very unusual. You'd almost imagine that most monitors were flipped, where this curved part would have been on the top and the flat part, where there might have been a little stand or whatnot, would have been on the bottom. And when we look at the back of the monitor, we can tell that they've actually flipped not just the outside of the case. In fact, there are 3 controls at the top, that almost certainly the entire PCB for the monitor is up at the top, flipped upside down, which is just different than most other monitors. Now, Leading Edge as a company, they did not design anything themselves. They simply resold stuff with their brand name stuck on it. That means that some other company designed this monitor, and obviously the team or the person who designed this put some real effort into this. They wanted this monitor to stand out, and I think they really succeeded. Just the little touches, like the fact that the front bezel is angled versus the seam here, where the case goes together, and then the fact that, as I mentioned earlier, the top is flat, and this cool kickstand design with this metal bar, the whole thing just screams effort was put into this. And I feel that they did a great job. This thing really looks cool. Now this is the leading edge logo, and you'll notice that it may not look like the leading edge logo that you're familiar with. This threw me for a loop last time I worked on one of these computers, and I didn't realize what was going on. I wondered why sometimes the leading edge logo had a blue background and sometimes it didn't. Well, it turns out that it has a plastic peel on it that no one has ever removed from this monitor. So I'm going to try to do the peel. Ah, yes, it's coming off. Sometimes these peels are very hard to remove simply because they have been on there so long. I mean, this one is no exception. The little corner got left behind, but there it is. There's the leading edge badge as it should have been. Looks great now. And it's funny to think that whoever was using this monitor over all those years never even bothered to peel that off. And I have to wonder how many people were using leading edge PCs and monitors and keyboards and never peeled that off and just thought that that's the way the logo looked. Anyhow, on the front of the monitor, things are pretty clean with the contrast, brightness, power switch. You could use a little UV flashlight like this one to try to figure out what type of CRT is in a monitor. And the fact that this one doesn't really show up with anything tells us that this is most likely an amber screen. Sometimes amber screens will show up as a yellow color, but if this were a green CRT, it would show up as a bright green. And if it was a white CRT, it'd actually show up as a kind of a grayish white color. The fact that it's not showing up as anything, yep, that means this is amber. Fortunately, we can see that this monitor has had a little bit of a hard life with some scuffs on the front. And I have tried to clean it because it was really dirty when I got the monitor, but the scuffs really aren't coming off. And unfortunately, when I was trying to remove the scuff marks, I was using some baking soda. That does a good job at not taking the texture off because the plastic is texturized, and Magic Eraser can actually just create a shiny spot. But while it lessened these scuff marks, there's one there as well, it definitely lightened up the plastic a little bit by removing some of the material. So that's always the danger when you have yellowed plastic like this. And unfortunately, it's a little bit splotchy as well. So this could probably benefit from a little bit of retro bright, but it also isn't that bad, so maybe it's not worth doing. This monitor does have two permanently attached cables for power and video, and the power cord is really unusually long. Not sure why, because I'm pretty sure leading edge machines had a pass-through for the monitor to plug into that would turn the monitor off and on. So I don't really get the reason for this. On the back plate, we have model number DR-1240, 117 volts. Using Google Lens to do a quick search of the FCC ID shows us this monitor was made by Daewoo Teletech Company, which coincides with the fact that it says it was made in Korea. The aforementioned controls that are available on the back are vertical hold, vertical size, and vertical linearity. And unfortunately, where the power cable and the video cable come through are not compatible with me adding a regular IEC jack like I did on the Apple monitor, so we're sort of stuck with these long cords. Kind of unfortunate. Now, since we know this was made by Daewoo, I'm very curious to know if anyone is familiar with these monitors being sold in any other markets in the world with different branding, obviously, because I think Leading Edge mainly was only selling in the US and Canada. So it's quite possible other manufacturers elsewhere in the world were selling this with their own brand, or even back in Korea, Daewoo themselves had a branded version of this monitor. So the next logical step on this monitor is to open it up and take a look inside. Now, of course, I have to give the caveat, don't open up a monitor unless you know how to do so safely. There are high voltages in there that can give you a big shock, especially if you plug in the mains cord. Well, then you might have 240 volts or 120 volts in there, which absolutely can be lethal. Please keep that in mind before you open up, well, anything that's plugged into the mains, especially if you're going to be sticking your hands in there while it's working. Oh, I just picked up the monitor to put the towel down, and there's something floating around inside. So that's extra bad. You don't want to necessarily be turning on a monitor like this if there are metal pieces floating around inside, because it could land on the board and cause a short. So you have to be extra careful with that. From what I've been told, when this monitor is powered on, there's just no image. So that tells us there's obviously some kind of a fault, but I don't want to turn it on and test it now. I don't want to risk potentially causing more damage by that piece of metal that's floating around inside of the monitor. Now it appears that there are multiple pieces to the monitor, and that this back plate where the wires come through might come off separately than the main part of the case, which will obviously separate from the front bezel once I get all the screws out. Okay, with a little pop, this panel has come free. The soot that you will often see inside of monitors like this comes from the high voltage potential generated during operation, and it really attracts this sort of black dust, which will form all over the nearby components. And with this area of the case, when it's installed in the monitor, it is very close to the high voltage anode cap on the CRT, which is sitting right there. Now, what's kind of cool about the design of this monitor is with that cover off, which is really easy to remove, you actually have access to potentially check for bad solder joints, which is a very common fault with CRTs that can often cause them not to work. And being that this is a monochrome or MDA standard monitor, you can tell that by the fact that It doesn't have pins 2, 3, or 4. That's the RGB pin. The circuit design of the monitor is quite simplistic. They actually have stuff somewhat labeled on the monitor. This section here says power. This is horizontal, and there's the flyback transformer. This is the video section, so this is taking the video signal and converting that into the analog signals to drive the CRT. And here is the vertical section, and it has the 3 potentiometers that are exposed through the back of the case. The section labeled power is quite small, and that's because with monochrome monitors of this size, they're almost always run by a transformer. And you can see the transformer here, I have my fingers on it. This takes the line voltage and converts it down of usually 12 to 15 volts, which then goes to the main PCB where the AC voltage from the transformer is rectified and regulated to the exact B+ that the monitor needs to run on, and then that's distributed to the rest of the circuit to drive the monitor. What I'd like to do is power this up so we can see exactly what the fault is, and I need to figure out what's floating around inside so we can ensure that we don't have any shorts. I guess luckily the fact that the PCB is upside down means when it's sitting on its base, the metal piece is probably down in the bottom of the case down there where there are no electronics. I still like to get that out of here though. All right, I didn't realize, but what has been floating around in here has already fallen out, and it's a little heatsink that was obviously installed on a transistor or one of the drivers on the main PCB. One thing that is concerning is inside the heatsink, I can see that the glue they use to attach this is the type of glue that I know is hygroscopic, so it absorbs water, and then once it does that, it becomes corrosive and conductive. And it's very common on these Korean-made monitors in the 80s for that glue to be all over the board. And unfortunately, if it's touching any of the leads of components, it can actually corrode them off the board entirely, which could easily be why we have a fault. In addition, whatever component this was, probably it's going to look corroded, whatever this was glued to, and that might also be damaged. But before we do any looking at the board, let's just power this thing up and see what it's doing. So for testing, I have my Pentium test bench with a monochrome graphics adapter connected to it, and it's currently connected to the RGB to HDMI. I just wanted to show that we definitely have a working system. I have a keyboard connected to it, so it's booted up. And on the back of the video card, I actually have a splitter. This is a 9-pin splitter, and that actually totally works because this is a TTL video signal. So I'm able to feed it both to the RGB to HDMI, and I can plug in the monitor at the same time so we can have both video sources working. That way we can see what we're supposed to be seeing on the monitor once I power it up. Okay, let's hit the power switch, see what happens. Well, I heard what sounded like high voltage maybe, but the power LED is not on. I can hear the hum of the transformer, so it kind of implies that maybe there's a short in there. And we can try using the spectrum analyzer app called Spectroid. I've used this a bunch of times on the channel. It's currently scaled from around 12K to 20K, and this monitor I think will run around 18 kilohertz, so we should hopefully see it. And when I turn it on, there appears to be a bit of a spike at 18 kilohertz, but it's way lower than it should be. And I'm noticing it looks like the power LED is not coming on when I turn on the power as well. So there's probably something wrong in the power supply section of the monitor. Now, something I could tell is that when I turned on the monitor, there was a hum from the transformer. So that tells me that the fuse is not blown. So I think the first thing I need to do is disconnect the transformer from the main board and measure the voltage coming in on the transformer when I turn on the power switch. And to do that, I used a couple nails in the connector on the transformer and a few clip leads into the multimeter, set it for AC volts. And when we turn it on, 16 volts. That looks good. That's what I would expect for an unloaded AC transformer that probably is going to be used for a monitor that runs around 12 volts. Now with a power supply like this, the AC volts comes from the transformer, and then that goes right into a bridge rectifier because it needs to be converted into DC so the power supply can do its work. So it's worth checking the bridge rectifier. There are basically 4 diodes connected together, and look for any that are shorted or open. What you should see when you're using the diode test mode on your multimeter is around a 0.6 volt diode drop on each of the 4 diodes that are inside the bridge rectifier. And that's what I'm doing here, and it actually does appear that we have a problem with one of the diodes in the bridge rectifier is just open. Usually they fail short, which is pretty destructive, but in this case it failed open, which is actually good. Now because we're missing one of the diodes, there's pretty much no way this thing is ever going to work, so we're going to have to replace this bridge rectifier. But what we can do in the meantime is just bypass the entire bridge rectifier by feeding DC directly into the power supply circuit. When you have a working bridge rectifier, you can actually just feed DC directly into it and it will work just fine. You'll have a bit of a voltage drop across it, but otherwise it's going to work. But we can just bypass it by clipping my bench power supply directly onto the output of the bridge rectifier, which basically goes into a large capacitor, and then we should be able to run the monitor that way. Now, I don't really know what the rectified voltage is after the AC transformer gets loaded down and then converted into DC, but I'm going to start the bench power supply at 12 volts, and we'll see if the monitor shows any signs of life. We'll use Spectroid again when I power on the monitor to see if we see any further activity on the spectrum analysis, but with the monitor powered on right now, it doesn't really look like it's working. Oddly, we have two peaks, one around 15 kilohertz and one around 18 kilohertz, which doesn't really make sense. This monitor definitely would run at 18 kilohertz, so that 15 kilohertz must be some other oscillation that's just being picked up by the phone. I wanted to add that while the bench power supply is powered up, the monitor right now is consuming around 639 milliamps at 12 volts, which just seems a little bit too low. Now, a good way to validate that the power supply is actually doing something is just look at the circuit design on the bottom. The traces that come out of the power supply circuit, they make their way to a capacitor, which is going to be filtering the output and giving some bulk capacitance. And if I measure the voltage across that, basically we have nothing. So it really feels like this power supply is just not working at all. It's just getting nothing out of it. Now I have to question, is it not working because there's a short or excessive current draw coming from one of the components on the main board? It's quite possible. Since I still don't know where the fault lies, if it's the power supply or something else, I'm going to attach my bench power supply directly to the output of the power supply circuit. So essentially that big capacitor that's on the other side of the board that the main power supply in the monitor goes to, I'm just going to feed 12 volts directly into that. And then that way on my bench power supply, I can see exactly how much current draw there is when I turn it on. First, I'm going to start with the main video cable disconnected. So that means the monitor is not going to really try to run. And I have the power supply set for 12 volts. I have it set for 2 amps. And let's see what happens. No, it immediately went into current limiting mode and it was giving the monitor like 5 volts. And if we plug the video cable into the output of the computer, and I'm going to up the power supply amperage to about 3 amps. Okay, so yeah, it's also drawing an excessive amount of current. That just seems way, way too high. There's something very wrong. I've switched to the top-down camera so we can take a look at the different subsections of the board. So power regulation happens here. There's the power input, bridge rectifier, the voltage regulation circuit, and this is the transistor, the pass transistor that bleeds off any excess voltage. The output of this, which is the emitter, is actually the B+, where it says the word power. This goes to the various subsections of the monitor. So if we follow this trace, it goes to test point 1, this is for testing B+, it goes across a jumper link into the horizontal section. Similarly, it goes across this jumper link into the video subsection, and it goes over here across this jumper link into the vertical subsection. So vertical deflection, horizontal deflection, and the video section. That's it. This monitor only has these 3 subsections. It's pretty simplistic. Now it appears that we have excessive current draw, at least in my opinion. So what I'm going to do is I'm going to connect the DC power supply back to the B+ rail, so I can clip on right here for the positive rail, and then the minus rail I was just clipping on right here. There's a big ground point. And we can use this multimeter with the sharp probes I have on here to check for voltage drop across these jumper links. I'm assuming these all have the same thickness. And the reason why these jumper links are here is because if I remove this jumper link, it will disconnect the power to the entire video section, or similarly horizontal or vertical. So with the bench power supply connected, I'm going to put the probes across the jumper link that goes to the horizontal section. This is going to be the highest current draw section of the entire board. Okay, let's turn this on. So we are getting like 1.6 millivolts, so basically nothing, very low, which makes sense because this circuit's not really running when we don't have the video cable connected. Let's check this section, which is vertical. Almost basically nothing. So that tells us that right now when we power on the monitor, really nothing's happening over here or here, which is fully expected, but yet we have this insane current draw. But yet we have a very high current draw, which sort of implies the only thing left is this video section. Let's turn it on. Yeah, look at that. Crazy amount of voltage drop across that jumper link. So I feel that whatever fault exists on this monitor right now is in this video subsystem. So I think what I'm going to do is I'm going to disconnect the power to the whole video section, and the monitor should still run. We should still have deflection, horizontal deflection and vertical deflection. If we power up the monitor and I connect it to the computer, the video cable on the computer, we won't have any video with this whole section disconnected, but that should give us a starting point on where to look exactly. And we have one IC various components. It's nothing too complicated here. And this must be a connection, probably wires that go to the neck board, or there's no neck board, the connector on the CRT. Well, I have to say it's kind of hard to solder onto this, and that's probably because of all this dirt and oxidation that's on here. But I've removed one leg of the jumper link, so I'm going to use these to try to disconnect it. So slide this off like so. Oh, and you know what? That's actually a resistor. Oh, right there, R79. Well, that actually now explains the voltage drop we were seeing, doesn't it? Okay, there we go. I've lifted the resistor. So that means there should be no power at all going to this video subsystem. Now, I should have measured the resistance of that resistor, and I didn't. But let's see what we get for the B+ now when I power up the monitor. All right, that didn't make a difference at all. Still have the same exact problem. I'm wondering if that means I should just disconnect the power to both the other stages as well, because maybe the whole problem of the excessive current draw is happening inside the power supply circuit. I don't even know why I didn't even think of that. It's probably being drained off in this thing. But to be 100% sure, I'm just gonna disconnect that jumper link and this jumper link. I suppose before we do that, let's just check to see if these are resistors or not. That is not a resistor, that is definitely a jumper link. Pretty sure this is a jumper link as well. Yep, they're both jumper links. That jumper link is disconnected now, that jumper link is disconnected, and this resistor is disconnected. So theoretically, none of the board is even connected to the power supply any longer. So with the bench power supply connected, if I turn it on, oh yeah, now we're getting almost no current draw at all. We're getting 16 milliamps at 12 volts being drawn, and I guess that's just coming from, I don't know, the little bit of the regulation circuit that's there. Okay, so which section of the board has the fault? Well, it's obviously not the video section, because disconnecting that resistor didn't change anything. It's one of these two, and I'm gonna wager that it's gonna be the horizontal. This is definitely the biggest current draw of the whole board. I can test that by just reconnecting the vertical, which has now been reconnected. And if I turn on the monitor now, yeah, it's like 80, 100 milliamps, almost nothing. Oh, working on this monitor is dirty and a pain in the butt. I think I'm gonna just disconnect all the cables here because I'm really struggling. Okay, well, since we can finally see the top side of the board, we can make some visual inspections. And something is very obvious here. The bridge rectifier, which obviously is where that little heatsink was, that clearly fell off a long time ago. And look at how burned the PCB is. That little bridge rectifier was running very, very hot. You can also see that circuit glue I talked about is all over the board. There's a bunch right under this cap. That's probably okay. There's some holding these two capacitors together. It's probably fine as well. Generally, it's a problem where it's touching leads. And I definitely saw a little bit. See how it's down on that resistor there? It's discolored. So that's an example of it corroding things away. You can see that this board has a couple 555 timers on it. Pretty cool. There is another example of crustiness on that resistor from that glue. It also could be affecting that jumper link. Otherwise, actually, it's not too bad. Okay, so I bet people were screaming at their screen. This capacitor, it was just sitting there in the bottom of the board. Okay, this obviously came from that spot right there. We can see that this Sam Young cap, it's all lumpy. That is a bad cap. Wow. And this is a 25 volt, 10 microfarad bipolar cap. Do I have any of these? No, I don't think I do. I might have to go look at my old CRT boards and try to find the replacement. This is C64. Well, that's gonna keep the vertical from not working. And maybe this was kind of connected to the board, and when I was jostling it around, when I was initially testing it, it came off, and that's why the power usage kind of went so out of control. So far we have two failed parts, the bridge rectifier and this bipolar cap. The two resistors that have crusty legs, that one and the other one was where? Down there, right near the cap that popped off. Those actually seem fine. I checked them with the multimeter and I don't see any issues whatsoever. Okay, I'm gonna go in search of another bipolar cap. I'm gonna take it from another CRT board and hopefully I can find something. Okay, I found a 6.8 microfarad bipolar cap. 7 microfarads, close enough. The voltage rating is 25, which is the same as what it was on the original, just the capacitance is less. Let's just see if this lumpy thing is even working at all. Nanofarads? Yeah, so that cap is completely dead. Kind of feels like this monitor has had a very difficult life, and judging by the fact that there was all that heat around the bridge rectifier, means clearly this thing was used after that little heatsink fell off, which is kind of curious. But I suppose that's one of the problems with having the board upside down. And I guess part of the problem is I have to look at footage to see if that cap was sitting in there. If you noticed it earlier, definitely shout loudly right now, so I know that you saw that and I should have paid closer attention. With the cap back in there, it's time to reconnect the jumper link that powers up the vertical section, because clearly this thing might have a chance of actually working now, but that is only if I reconnect all the various cables, like the ground lead to the CRT, and these deflection yoke cables, which I didn't really pay attention to which went where. Usually red is the horizontal, and judging by the way this wire is bent like this, I think it's going to connect right over here. And in fact, there is a G and a Y on the PCB that definitely confirms that these connectors are connected the right way. Okay, all that's really left is this front panel connection here. I think it's contrast and brightness and the LED. I'm gonna leave the CRT disconnected right now. And I have the bench power supply connected. I'm at 2.4 amps. It's unplugged from the computer. Let's turn this on. Yeah, 800 milliamps. Oh, much better, everyone, much better. I think I should reconnect the CRT because that has the heater that may or may not come on until there's actually a signal from the computer. I'll put my gloves back on, keep my fingers a little cleaner. Okay, we are ready to turn on the power now that the CRT is connected. We're at 900 milliamps. Seems okay. It's pretty stable as well, good. And now I'm gonna connect the video cable. Let's see what happens. Here we go, 3, 2, 1. We're at 1 amp. That's a good sign. It's not excessive, at least. Oh, look, we have an image. Oh, it freaking works. Sorry for the flicker, it's running at 50 hertz. It's there. It's freaking working. Look at that. Awesome. That is so cool. It was just one bad bipolar cap, and obviously the power input section is bad, but that's so awesome. I was thinking it was dead, and then I was turning the knob up, and all of a sudden it came into view, and I was like, it's freaking working. That's so cool. And one thing we can tell for sure is that the deflection looks good as well, and that's at 12.0 volts, and it's just over 1 amp right now. That's all the current that's being drawn. So I think I have the B+ set correctly. If we turn down the voltage here, I'm going to turn it down to 11 volts. The deflection came in a little bit. Let me change the camera to not flicker so much. So with something that's full screen shows you the deflection a little bit better. So typically when you lose voltage on B+, you lose the horizontal deflection. Now we're at 11 volts, a little over 1 amp is all that's being drawn. I'm going to put it back to 12 volts. And there we go. Now we have a much more square image, which is much more correct, much more close to probably what it should be. Now it's possible that B+ should be 12.5 volts, 13 volts, who knows? But 12 volts certainly seems to work well enough. And the image, it's looking decent. Okay, now we're displaying a full white, full bright image. What I can see absolutely without a doubt is there is burn-in on this screen. I can see little stripes, and it wasn't displaying a static image all the time. It just was displaying text, and that text has resulted in burn-in, which is not unusual. It just means this monitor was well used, and we could really tell that by all that soot that was inside. If it was all clean inside, then it would have been very unusual if this thing had any burn-in. I do have to have the controls maxed out, brightness and contrast. So this is the contrast control, and this is the brightness control. And the contrast control most likely controls the intensity bit. So there is a test pattern, split screen, number 5, and this is what I'm talking about. So see, this is the contrast control. It doesn't affect the bright part of the image. It only affects the darker text, which is very common for the way monochrome video actually works. Now, one other thing that's very interesting is that the power LED is on, but it's very dim. I guess that's just the way it is on this monitor. Power switch here doesn't do anything. Well, of course it doesn't, because the power cord is disconnected from the wall. I think the thing to work on next is to try to fix the bridge rectifier. I need to find a replacement that I can swap out, something that will not overheat and die. And maybe now that there isn't excessively high current draw, this power supply circuit is actually going to work. It's probably fine. It's just that it's only designed to supply whatever the 1 amp the monitor needs, and when it was drawing 3 amps because of that bad cap, that was causing this to just look like it was outputting nothing. All right, I went and grabbed a bridge rectifier off an old scrap board, and obviously the footprint is not compatible with what was on the board, but this is a much more beefy bridge rectifier. Now hooking this up is quite easy. If I just fold this over, you'll notice the 2 middle pins are AC input, and then positive and negative are the output. And on the board, it's quite easy because the negative and positive are labeled appropriately, and the other 2 pins are AC. And because I use some solid wire, this thing is actually very well supported, but it's also free floating, which means that even if it gets warm, it's not going to get hot around anything else. And remember that this bridge rectifier is not handling 120 volts. It is only handling like 16 volts, whatever comes from that transformer. So I'm going to plug this into mains, turn it on, and we're going to use the multimeter just to check the DC output voltage of the B+, see if that thing is actually regulating. So I'll just connect the positive probe to that test point we saw on the top. I think you can just make out what that says. Okay, here we go. 3, 2, 1. 11.3 volts. So I guess 12 volts was slightly over voltaging the whole monitor. And it took a little bit of time to warm up. But there is our test pattern. It's working. Now I almost feel that this is maybe a little bit too low. Maybe this should be 12 volts. It seemed to be working a little bit better, although I don't know, it looks like it's fine even right now. I may just adjust the B+ up slightly, maybe closer to 12 volts, just to give it a little bit more horizontal deflection. And we'll do that monitoring the test point. Okay, that's down. Okay, we're at 11.9, 12.0. Yeah, looks a little bit brighter, if anything, as well. But what this definitely confirms is the only thing that was wrong with this, well, there were 2 faults. The bridge rectifier had failed just because the heatsink came off, but also that bipolar cap had fallen off the board, and well, put a new one in, salvaged from a different CRT board. This monitor is fixed, and was a relatively simple fix as well. Cool. All right, I ended up turning the B+ down to about 11.8 volts, a little closer to what it was originally. I don't know, I feel bad just running it a bit higher than it should be run. Now the monitor has run for a few minutes. I'm just gonna power this off. I wanna feel the temperature of the bridge rectifier that I installed, and it's definitely pretty warm. It may benefit from a small heatsink being installed on it. You know what, just for grins, I took that bridge rectifier off this board and it didn't have a heatsink on it, but I think I'm gonna steal one of these heatsinks off of one of these packages, and I'll just bolt it on because there's a bolt hole on it. I'll bolt this on to the rectifier just to give it a little bit of cooling, and one that will never fall off. All right, there we go. Lock washer and that heatsink has been attached. That should give this sufficient cooling forever, I guess. If you have one of these monitors and you're looking to do some adjustments, this adjustment right here, this is the width control. You're gonna need a plastic tool to adjust this control. That's the focus control. This control, VR53, you can see just the hole right there. That is the G2 control, so it's like the screen control. Turning that up is like turning the brightness control up on the entire monitor, and I did adjust that a little bit just to bring it up slightly. Over here is the B+ adjustment. That's what I was adjusting before to adjust the overall regulation. Test point 1, TP1, that's where you can measure the B+ that's coming out of the power supply while you adjust that. I adjusted it around 11.8, but it was 11.3 originally on this board. Don't know what's actually correct without the service manual, but that's good enough, I guess. You can see up here at the top of the board, this was the bipolar cap I replaced, which should be a 10 microfarad at 50 volts. I put in 6.8 because that's what I just had on hand, and whatever, good enough, it works. And there is another adjustable coil. I don't know what that one does. I didn't even try to adjust it. This is the right tool to adjust it, but this one adjusted the width, so I just left that one alone. And I just ran this monitor for several minutes, and I felt the temperature of the bridge rectifier with that heatsink on it, and now it's just barely warm. So clearly a little bit of heatsink will go a long way keeping this monitor running for a long time. The monitor is all back together. Let's turn it on. And I've been using it for a couple hours now. The thing works absolutely perfectly now. Maybe it's a little bit dimmer than it would have been when it was brand new, but it's really hard to know if that's the case or not. But everything else about this monitor is working great now. Up on the screen, we have CompuShow version 9.0, and I've created some images to display on this monitor. Now, these are 720 by 348, which is the native resolution of Hercules graphics, 1-bit color. And if we push F8 to show these images, look at that. It's interesting that back in the day when Hercules was common on low, inexpensive computers, I don't remember ever looking at any pictures on it that actually looked decent. And the funny thing is, the Macintosh showed that it was quite possible to have decent grayscale approximation using Floyd-Steinberg dithering, which is what I did to create this image. I used GIMP on my main computer. And this really does look pretty darn good. Very similar to what you'd see on a Macintosh. Of course, the big difference being this is an amber screen versus white. And if you've ever been to Chicago, you'll know exactly which picture this is. I took this photo on my last trip there. This is colloquially known as the Bean, and it's a reflective art installation. And it's absolutely awesome to see in person. And it's a decent representation of the Bean on this Hercules display. It actually looks pretty good. Moving on to the next picture. This is another picture I took recently in a parking structure, and I just converted it. And you have to adjust the levels a little bit when you convert to monochrome 1-bit display like this. I think that looks pretty good. It's a decent representation of the grayscale nature of this concrete parking structure. And here's a photo of an ATI Solutions Rev 3 card that I worked on in a recent second channel video, and I showed this off on the main channel video inside of the PC XT clone from NCC. And again, I think this picture comes across on this monitor looking really quite good. And then here's a photograph I took of the Steel Bridge here in Portland. That's one of the many bridges we have over the Willamette River. This is a very old bridge that actually can take foot traffic and bicycle traffic on the lower level. And then this whole deck can raise up and allow ships to pass through. And on the upper deck, you have cars and light rail. And then here is another picture of one of the incredible Gothic buildings in Chicago, downtown Chicago. It's just the top of it with a US flag on the top. It looks amazing, although the real deal, the actual color picture looks a lot better than this monochrome representation. And then here's a photo some of my Canadian viewers may recognize. I took this photo in downtown Vancouver, and it was a nighttime photo, hence the reflection off the water, although this didn't really translate super well to a monochrome image. I probably should have darkened it a little bit more so the sky wasn't so light. And I think this is the final photo. I took this picture of a man in a hospital waiting room. Who knows what's actually on his mind? Hopefully it's nothing horrible, but he definitely looked like he was deep in thought when I snapped this photo. And I must say, even in 1-bit monochrome with dithering, I think this comes across really quite nice and still conveys the original message of the photograph that I had taken. And that's it. We're back to C-Show here and exiting the program. I mean, everything works really well. Let's run Planet X3 in Hercules mode. And it doesn't look too bad. We're not getting the full image because these are CGA assets, I think, and they don't exactly scale properly to the 348 pixel lines, which is why we have bigger borders at the top and the bottom. But the game works, although it goes without saying that with dedicated assets for Hercules mode, it would look better filled up without these extra lines that come from the scaling that you're gonna see. But it doesn't really make sense to do that because very few people are gonna be gaming on a Hercules graphics subsystem like this. And let's try out one last game that is Fast Doom running in Hercules graphics mode. And it's interesting, it uses a custom mode because the image is actually off the top and the bottom of the image. So this must use more than 348 lines. And keep in mind, I'm running this on a Pentium, so there's really no performance implications from a slow CPU. So even though we have a slow video card, that's not really causing any issues. And you know what? This actually looks really good. Oh, I must have the floor textures turned off since everything looks flat. There we go. I changed it to high detail and I turned the floor and ceiling textures back on. And look at that. That actually looks quite good. I mean, wow. I'm amazed how fast this is and how playable this is. This is not bad at all. Pretty cool. I have to say, I've never tried fast Doom with Hercules graphics mode, and I am playing with the keyboard, which I don't normally do. People always complain like, oh, you're such a terrible Doom player. Well, it's because I'm using this little keyboard and not the normal mouse with WASD that I typically play Doom with. So this thing is not really set up to, well, I'm using the arrow keys. It's just not an ideal way to play, at least not for me. I'm just not used to it. It looks like we might be doubling the 320 pixels all the way up to 640, so we're losing some pixels on the sides. And I wouldn't be surprised if this is actually running in 400 line mode using a special custom mode, because the 6845 can be reprogrammed to do that. And I need to adjust the vertical size control on the back of the monitor to bring this in so that we could see the top and bottom of the image. But I am completely flabbergasted as to how good this absolutely looks. I wouldn't want to play Doom this way because you can see that it gets really dark in this area, although maybe we could adjust the gamma to fix that. Let's just give that a quick try. You know, what's kind of interesting is I don't see an option for gamma. Interesting. We are getting 35 frames per second though, so we're maxing out the speed possible with Doom. It really can't run any faster than this, not the versions on DOS at least. Let's just finish up the level while we can. Yeah, it's a little hard to read the red text in monochrome, but still, we're looking at this on a Hercules graphics monitor, and I'm absolutely stunned how good this actually looks. Wow. Okay, that's gonna be it for this repair video. Another monitor saved. All we had to fix was this bad bipolar cap, which kind of fell out of the board. Sometimes the problems just sort of fall into your lap. And that's definitely the case with this cap. And then we had this damaged bridge rectifier on the power supply circuit. And it's good that this didn't go short, because when these go short, they actually can cause some damage on the monitor because they will inject AC directly into a circuit that is expecting DC, and that causes all sorts of bad things to happen. Like you can blow up capacitors, things like that. So I'm really glad that this was only open, which just sort of caused it not to work. And once we fix that excessively high current draw because of this bad bipolar cap, well, then the original power supply with a replacement bridge rectifier worked perfectly. And I guess it died probably because this heatsink fell off a long time ago, and that poor bridge rectifier was running at a zillion degrees, which caused all that burning on the PCB itself. Otherwise, this monitor really is in great shape. All the original caps and every other part on there is perfect. I did scrape some of the glue away from those two resistors that had a little bit of corrosion on there and just sort of cleaned it up a little bit, so that shouldn't be a problem at any point in the future. And I didn't see any more of that glue on any other components other than the edges of capacitors and things like that, but that's usually fine because they're covered in plastic anyways. It's not like it's touching metal. So this monitor should keep on working for a good while longer. I'm really glad to have been able to save and fix this monitor because, as I mentioned, this thing was about to be recycled, and well, as we can see, it's working great and with minimal fuss or effort. I didn't even spend any money on the parts because I just took them off other boards that I had in my scrap bin, which is why I love keeping scrap parts, because you never know when you're going to need something like a bipolar cap, and that fixed this monitor. So if you enjoyed this meandering video of me trying to figure out what was wrong with this monitor without having schematics, I'd appreciate a thumbs up. But if you didn't, you know what to do. Huge thanks to my supporters. Their names are scrolling up the side of the screen. They make it possible I do this full time. And you can become a supporter too if you'd like. There are links down below. Subscribe if you haven't already, all the usual YouTube junk. And I guess that is going to be that. So stay healthy, stay safe, and I will see you next time. Bye-bye.